So thanks a lot to everyone for the organizers for inviting me. I've met a lot of great people and it's been a lot of fun. Okay, so I'm going to talk about this game called reglog for regular logic. And okay, it starts with this very good-looking man doing something very important. So what is he doing? He's playing with logic somehow. That's what we're going to say, at least. Okay, so the following has very little relation to the movie Minority Report. It's just an analogy. But in this movie, we have Detective Tom Cruise. He's playing seamlessly with logic. He's got a database, and he's able to kind of connect relevant ideas together to solve crimes. So we want to have our own version of this, and I'm hoping one day there's this game called Reglog the Game, and so that's what this is brought to you by. So imagine you're an investigator on a case, and you're adding to and you're narrowing down a set of suspects to find who did the crime. And so you can pull up cells from your computer's database. So you've got this cell called My Suspect. You pull it up. You connect it to a cell called Acquainted With. You attach them together, and you define a person of interest to be the result. So this is a wiring diagram where we have two cells, My Suspect and Acquainted, and they're connected, and I'm exposing the person that is the person of interest. It's someone acquainted with My Suspect. And I'm hoping that this looks like something that regular people could use without having to know any logic. They just connect things together. So you can add to this world, you can add to your system some beliefs about the world, like that if a person works at a company and that company is a startup and another person works at the same company, so they're all together here as one company, that entails that the first person isn't acquainted with the second person. So you can add beliefs about the world in this form. So you might have another belief that says it's true that my suspect is acquainted with the victim. This thing has no external ports, so it's just a truth value, and the truth value is true. So this is how Tom Cruise plays with logic in my version of the story. You can nest concepts together. So if you have this wiring diagram here, ABC, and you have this wiring diagram here, you could take the C1 and C2, and since they have the same shape, the external box here, this external thing, has the same wiring, like 3 ports exposed, and that's what C needs. You can plug it into C and get that thing there. So you can compose, and so inside of A, there might be a huge nesting of other concepts. Okay. You can click a cell to see what's inside. And you see that the victim is a person, but the person is some kind of weird identifier. P105 and P820 are your victims. That's kind of weird. So you actually want to see facts about them. So you connect this fact table up to it, and now you expose the person, but you also expose their first, last name, and their height. And you see that your victims were Alice Hu and Bob Barr. And Alice Hu, you know her height was between 5'10" and 6 feet. But Bob Barr, you don't know his height at all. It's just some unlabeled identifier. So I'm going to give math for all of this stuff later on in the talk, what all this connecting of things and what these databases are and all that sort of stuff. Some knowledge could be missing or imperfect. And the machine knows some basic logical reasoning, like it knows that if a strong person is also a fast person and you want to see that person, that's a strong and fast person that you want to see. And you can manipulate diagrams by combining or breaking up these intersectionalities, intersecting strong and fast, or by breaking dots. So if you have a dot like this and you want to break it, you can kind of separate it out, or you can break this one in various ways. You could break it in other ways as well. And what these dots mean is that these 3 ports, X, Y, and Z, are all equal on this side, whereas on this side, we've only required that X equals Y, and Z is just anything. So over here, if X equals Y equals Z equals W, then we've got like X equals W and Z equals Y. And the entailment says that if all 4 of them are equal, well, certainly these 2 are equal and these 2 are equal. So those types of entailments are things that you can do as Tom Cruise. So this is just regular old logic. You just have equality and exists and stuff like that. But you've got this mathematically specified GUI. Finally, so you've identified certain sources of and constraints on your suspect. You know that Sue's a suspect, so you have a source of suspects coming from some area. You've got some constraints, like you know that your suspect is acquainted with the victim. And so to catch the suspect, you chase them. But that's actually supposed to be a hilarious pun. Namely, the chase is the name of an algorithm for database theory. It starts with a database instance with knowns and unknowns. You add axioms like every two people who work at a startup together were acquainted at some time. And so this would be written as for all P and P prime of type person, if there exists a company such that person works in the company and person prime works in the company and the company is a startup, then there exists a time such that P and P prime were acquainted at time T. So you could write these things, but you can also write that in this regular logic. This is a regular logic sequence. It's also called an embedded dependency in database theory. It's also called an existential horn clause in logic, and it's also called a lifting problem in algebraic topology. So the same sort of structure, this probably should have been an implied symbol here, but the same sort of structure, regular logic sequence, have been named by many different communities over the course of the last 50 years or so. So they've all kind of rediscovered a common fragment of logic called regular logic. So this chase takes these axioms in this database instance I and says, what is the minimal repair, is what people in database call it, I prime, some new instance that includes the old instance but conforms to the axioms. So you'll take your instance plus a bunch of axioms and find the minimal instance that conforms to the axioms and contains the original instance. And this is called the chase. So now to complete this story, you've created this important cell, the locations that your suspects could be in, and you connect the location port of that cell to your autonomous car's location port, and it drives you to the place. And you find the suspect. Oh, you got promoted to Tom Cruise. You were just you before, and now that's it. So I'd like to make this real, but I don't know how to make this real because I don't know how to program computers. Especially like I don't know any dependently typed languages, and I think that this would require one, but I'm not really sure. So Detective is not the only game that I'm going to talk about. I'll talk about a bunch of other games besides Detective, but in the meantime, I'll talk about a bunch of mathematics and how the math connects to the user interface that I described above. So the math is a bit technical, so I'm going to try to go through it, parts of it slowly and parts of it fast. So I hope it's not traumatic, that like by the time I'm done with the math and back to these other games, that it's not something that you are now like unable to even think anymore because it was painful or something like that. I'll try to talk about it in a relatively gentle way, but it's somewhat involved. So anyway, but the idea is that category theory can be used as a specification language. So it helped in the development of Haskell, as I think most people know, but it can also be used to specify DSLs that aren't Haskell, or Idris or any other thing. So for example, there's someone named Tom Ellis who made a Haskell package called Opali, where I guess you can do type-safe queries. And it's based on some of my work from 2013 or so, that the stuff I'm talking about today is an extension of. So the idea is to take these category theoretic concepts and use them to specify a programming language or a DSL that you don't have to think through all the corner cases ahead of time because they've been thought through by the math. And the math involved is what's called regular categories and regular logic. So there's a strong connection between category theory and logic. Every sort of category has a kind of logic that it can understand. So a topos has higher order logic. If you've heard of toposes, they are the place where higher order logic makes sense. A Cartesian closed category, I probably should have started with that, is the place where a lambda calculus makes sense. So if someone has a lambda calculus and someone else has a Cartesian closed category, and every type in that lambda calculus has an associated object in the Cartesian closed category, and every function in the programming language has an associated function, the Cartesian closed category. That means that the Cartesian closed category can interpret everything that you write in the lambda calculus. It knows what you mean by that stuff. It knows what tupling means. It knows what function types are. It knows what composition is. So a regular category is another type of thing. It's not a Cartesian closed category. It does have products, but it doesn't have function objects. So in those bubbles, I was never taking the set of functions from one relation to another. But I was taking what are called finite limits, which are the terminal object, a unit type, and pullbacks. Pullbacks are if you have three types, A, B, and C, and a function from A to C and a function from B to C, you can form the type of all A, B pairs who agree in their map to C. So all A comma B, such that f of A equals g of B in C. That's the pullback type. So if you have those and you have images, so you can take any type and you can see all the things that are hit by your function. So you have a function, you find all the things in the codomain that are hit. That's called an image. And a regular category is basically something with finite limits and images that play well with finite limits. So you don't have to know what this is, and Hask is not one of these. I don't think Hask, I don't know if it is, if it has image factorizations. But for our DSL, we don't need it to be Hask. We're going to make our own DSL. And so regular logic is and so we're going to talk about regular categories. And regular logic is the internal logic of regular categories, just like lambda calculus is the internal logic or language of Cartesian closed categories. So there's lots of regular categories that, in my world of math, the category of sets, which is a lot like type, I guess, any topos. Set op is a regular category, the opposite of any topos, the opposite of the category of topological spaces, the category of groups, the category of rings, or any algebraic theory, monoids, modules. You can take a regular category and look at all the functions into a single object. That forms a regular category. And if R is regular and C is a category, then R to the C is regular. So I don't know, I think the audience here spans a big spectrum in terms of categorical sophistication. So in terms of all this stuff, you may have understood 1/5 of it or 3/5 of it or whatever. There are probably people who understand all number of fifths of this here, I hope. But it's okay if you don't understand all 5/5. So category, how to think of them, in some senses, they have a good notion of relation. So here I use this fancy thing called a two category, which might sound like I'm getting really fancy here. But you probably learned about relations in early CS class, where you have two sets, A and B, and a relation is just a sub-object of A times B. And when R is a regular category like sets, then relations work really well. You can basically compose them, and they form what's called a locally compositile two category. So you can compose relations, and you can, you can compose and compare them. So what is this two category thing, really briefly? If I have a relation and you have a relation in A times B, mine might be a sub-relation of yours. Like I have a database, I have a table, you have a table, and mine is a sub-table of yours. So that is what this two here is doing. It sounds way too fancy for like how simple it is. All that's going on here is that I have types like A, B, C. I have relations between A and B and between B and C, and I can do a join to get a relation between A and C. That's the composition law in this thing. And I can compare two relations. I can say one is a sub-relation of another. Once you have that sort of thing, you've got a two category. So if anyone starts talking about two categories and you think that they're getting out of like the realm of reality, just think about relations, how you can compose them, and how you can take one relation to be a sub-relation of another, and now you've got an idea of what a two category is. In any two category, there's something called an adjunction. If you've heard of monads, monads and adjunctions are very related. And if you look at the adjunctions in rel, in the category of relations, you get the category of sets back. So if you're a novice category theorist and you want to like do something I think everyone should do at some point, and you could try to figure out why it is that set is the category of left adjoints in rel. If that makes no sense to you, that's completely fine. But okay. So regular categories have enough structure to do regular logic. And Regular logic is the notion of relations in regular categories. Okay, given relations R of x, y, and S of y, z, what is the composite relation? What is the join of these two tables? I'm going to join these two tables, and I'm going to project out the y. So it says, I don't care about the y. Just tell me, select from R and S those x-z pairs for which R of x, y, and S of y, z holds. So there's some kind of query that you can write down. And that's why Tom Ellis's Opali was based on something very similar to what I'm talking about today. So the and together with variable sharing is given by a pullback. This guy is, when I said pullback before, this is the set of all x, y, z's that have a common y. And the exists quantifier is given by images. So I said regular categories have images and pullbacks, and that's the stuff you need to interpret variable sharing, ands, and exists. So in lambda calculus, what you need to interpret product types is a product. What you need to interpret function types is a function type, function object. Here, what you need to interpret and is pullbacks, and what you need to interpret exists is images. So that's the sort of relationship. And you get the composite relation here. So in this graphical approach, if we have this regular category, then I'm going to draw this weird shell picture or here. Whenever I have a context, that's a logical term. But really, if I just have a bunch of objects of my category, so I have set A, R1, a set R2, and a set R3, and a set Rn. And if I have some bunch of sets, I'll draw a little shell like that. And I don't know if it's a good idea or a bad idea to call the fillers of shells cells, but I did. So I have a cell whenever I have a sub-object of this thing. So in my regular category, I have these n types. And now in the product type, I take a little relation, and I call that a cell in this type. So this type is holding all the fillers. Oh, I lost battery. Okay. All the fillers for that shell are the sub-objects of that relation. Okay. And the wiring diagrams denote combinations of finite limits and images. That's what they mean. That's the meaning, the semantic meaning of a wiring diagram. So let's discuss those. So this is a wiring diagram. I can no longer point, but what is it? No, yeah, oh, I can. Is that the thing? You can see it? Oh, okay, great. Yeah, so we have these three cells, and we have this outer cell. What is the type? What is the mathematics of a wiring diagram? It looks like a picture, but it's actually a specification of who's connected to who. So it's a morphism in the operator of cospans. I should have said cospans there, sorry. But what that means is it's just this picture up here. So we have gamma A. It's type 1, 2, 3, 4, as you can see over there. And you have gamma B. That's type 1, 2. So there's 1, 2 here. And there's gamma C, which is 1, 2, 3. So it's just counting the number of ports. And gamma prime, the outside thing, has 6 ports. And then who's wired to who are the U, V, W, X, Y, and Z, and T. So you can see that the outer 1 and the outer 2 are both wired to T in the picture. Gamma A, his 1 port is wired to U, as you can see, and gamma prime's 3 port is wired to U, as you can see. So this is just some finite sets and some functions between them, and they specify a picture like that. They don't specify where gamma A is on the page, but you could move it around and still have like the wires connected appropriately. And the wire connections is all you need for the logic to work, as I'm sure it's not too hard to notice. So a cospan is just such a thing. It's a pair of functions with a common codomain. So I have this set gamma A plus gamma B plus gamma C. I have this set gamma prime, 1, 2, 3, 4, 5, 6. I have this set T through Z, which is the set of variables that are being shared. So a cospan is just a picture like that, either on this side or on that side, depending on how you want to draw things. And we can convert a wiring diagram like this into a logical expression. And this is a slightly annoying to write down, but the logical expression is on the bottom. O of like T, U, V, Y, Z, because there's 2 T's, a U, a V, a Y, and a Z. is, so you say for every unexposed wire, in this wiring diagram, you can see that W and X are unexposed. The outside world doesn't see them. So for every unexposed wire, you write an exists. So exists a W of type W and is X of type X, such that, and then you write an and of the remaining things. So Q of U V W X and R of W Y and S of X Y Z, S of X Y Z. And the fact that these two things were equated, T1 equals T2, is also anded there. So anyway, you can turn any wiring diagrams directly into a logical expression. So we both understand them, what they are set theoretically, and how to turn them into logical expressions. Here's a simpler example. So what would the logical expression for this be? The outer thing of xz should be what? There's one unexposed wire, and exists a y, such that q of xy and r of yz. Okay, so that's the basic idea. So what's a two category? Here's a little primer on monoidal two categories. A one category has objects, morphisms, and composition, like you have types, functions, and ways of composing them, and you have id. I forgot to write that. Identities. A two category adds a notion of two morphisms between one morphism. So we have this function a to b and this function g, f and g, and alpha is a way of comparing them. Now that doesn't make any sense in the category of types and functions, but it does make sense in terms of functors and natural transformations. If you have two functors, a and b there would both be Hask, if Hask is something I can say, Hask, the category of Haskell data types and functions. So if a and b are both Hask and f and g are functors, then alpha would be a natural transformation. Those would be the two morphisms in a two category. So we'll be working in the two category of relations where a and b are sets, f and g are relations between a and b, and alpha is a sub-relation. Or we'll be working in the category of post-sets where those entailment symbols live, where a and b are partially ordered sets, f and g are functions, monotone functions, and alpha is a natural transformation, which means that for every element of a, f gives me something in b, and g gives me something in b, and alpha says that the f guy is less than the g guy when you shoot it over. For every element of a, f of it is less than g of it. So that's another two categories. So two categories aren't so unfamiliar. You just might not have heard them called that before or thought about them in that way. But two categories can be opt or code. You can take the opposite of a two category or a category where you just reverse the arrows. So instead of going left to right, they go right to left. And the co reverses the arrows, the two arrows, so from down to up. So you just take any two category and reverse the direction, and it's just bookkeeping. And finally, in monoidal two categories, you can combine things. So given two objects, you can form a new object. So you can think about product types. Given two types, you can form a product type, or a sum type. Those are both monoidal relations. Those are both monoidal products. The idea is that they operate on objects and on morphisms. So if I have a function from A1 to B1 and a function from A2 to B2, it doesn't matter if you're doing sum types or product types. You get a function from A1 dot A2 to A B1 dot B2, from the sum type to the sum type or the product type to the product type. Either one of those is a monoidal product. It's a monoidal structure. And there's also monoidal units. So in the product structure, where you're multiplying things, you use unit. That's the monoidal unit. And in the sum types, you use void. That's the unit. Anything plus void is itself. So that's monoidal two categories in a nutshell. So this detective GUI can be understood as, and of course it's not really the graphical part, the part that actually is terrible. It's just the specification of it. But we fix it a set T. So this T will be the set of string labels like person, height, etc. And then there's a symmetric monoidal two category called cospan sub T co, which sounds really terrible again, but the objects are aritides. They're just an n tuple of types. So you pick a list of types. Those are the objects, and those are what those circles were. They're just lists of types, those shells. And a monomorphism is a co-span between a list of types and another list of types. So it's a list of another list of types and two maps between them. And that was that picture I showed a little while ago. The two morphisms are just maps between the wiring sets that make the diagrams commute, and those correspond to breaking wires. Basically, if I have a function, if you remember what the W stood for, it was like the wires. And if I have a map from W prime to W, then W prime kind of is like broken wires. Like if two things in W prime map to the same thing in W, it's as though we broke the wire going in the backwards direction. That backwards direction is the co there. That's what that's doing. We could also throw something in W away if we wanted to. So there might be something in W prime that wasn't, there might be something in W that wasn't hit by W prime, and you throw that dot away. Finally, the monoidal structure is given by concatenating lists. So if I have two shells, I can concatenate them and get another shell. And the monoidal category post set has its objects are post sets, its morphisms are monotone maps, and its two morphisms are natural transformations. I talked about that before. And this monoidal structure is that you can multiply post sets. So if I have a post set P and you have a post set Q, you can take P times Q, and you know what less than should mean there. If you have a P comma Q pair and a P prime comma Q prime pair, when should the first be less than the second? Well, if P is less than P prime and Q is less than Q prime. So now we can multiply post sets. It's a monoidal structure on post sets. So all the games I'll talk about, including this detective thing, will be a certain kind of two-functor from co-span co to post set. It'll assign to every shell a post set of all the little cells you can put into it, ordered by that entailment relation. So that's all the stuff I've been saying is encoded in that single two-functor. To each shell, we associate a post set, and we have an order that's entailment. And that's what the post set is telling us about. Okay. So the definition of a regular calculus is a lax monoidal two-functor from co-span co to post set, such that the laxators have right adjoints. Whatever that means. So you get these, you get these things here. So let me just denote by regular calculus the category of all these guys. It's a set T of types. These are string labels. We're almost done with this math part. A set T of string labels, a set P of Ajax functors, adjoint lax functors from co-span co to post set. And the theorem is that there's an adjunction between the category of these regular calculi, so the thing on the left, and the category of regular categories, such that when you start with a regular category, so you don't necessarily have to remember what all the regular categories are, what they mean, but there's lots of them. Toposes, opposites of toposes, sets, any algebraic theory, etc. So you take any regular category, you can turn it into regular calculus and come back and you'll get something equivalent to where you started. So that's the theorem. It says that any regular category can be specified by regular calculus. So we want software to do, or I want software to do this detective work, so I want just regulog the game. And in this game, we have this set and this Ajax two-functor, whatever that thing is, but it's well specified. So what is co-span co? The objects are these shells. They're encoded as lists of types. The monoidal product is multiple shells encoded as list concatenation. The morphisms are these wiring diagrams encoded as co-spans. The two structure is breaking dots and encoded by co-span maps. And then if you're a game developer for this regulog the game thing, you supply the P. So you supply for every shell what the elements of P of that shell should be, what the fillers should be. And you specify what it means for one filler to be less than another. And you specify for every wiring diagram how you're going to take fillers for those internal shells. You give yourself a filler for the external shell. You give yourself a formula. And then you ensure that composition and identity and dot breaking make sense. Once you do that, you have a game. And the possible games are as broad as all the possible regular categories. So In the back end, I think you might need some kind of database language, CQL or SQL. SQL is a categorical query language. There you might have like categories as database schemas, and instances or functors to set, and you can turn this into a backend by saying that every one of these dots counts as both a shell and a type. So this shell employee has lots of ports, one for every outgoing arrow, works in, first name and manager, of type, department, string, and employee. So anyway, the point is that there's a categorical backend that could work for this, where you can actually do the chasing and the embedded dependencies. So all of the regular sequence you write down, like two people are acquainted, means that they if two people work in the same startup and they're acquainted, you can encode those in this CQL language, and you can chase the EDs to actually do the work of like putting all of your axioms in. Okay, so let me just talk about I'll talk about a bunch of different games or a bunch of different regular categories, but I'll do them in terms of these game-looking things. So Reglog the game, in my vision of it, is actually a bunch of games. And what's in common is this same graphical user interface and same sort of interaction. Namely, you can create shells, you can attach shells, you can make wiring diagrams, you can compose wiring diagrams, you can zoom in and out of wiring diagrams. You can fill shells with content of a certain form to make cells, and you can click on cells to interact with the content, and you can do reasoning like entailment and dot breaking and substitution. So that's what's in common between all these games. But the differences are formally just that you have different functors from cospan to poset. And when I said that you fill the shells with content of a certain form, I meant the form specified by P. So some examples that we'll talk about are where are my keys, smart witter, partitions puzzle, Boolean circuit, solve equations, and more. Okay. So a simpler version of the detective game where the person doesn't have to think about the entailment, they're just querying, is imagine like, where are my keys? You tell Alexa Siri or Siri facts as you get them, and you sort your life. So you have this little bubble called where is, and you click it, and inside of there is all the things that you've ever put anywhere. Like your keys were put in the top drawer on the 23rd. The lease is in the file cabinet. It was put there on the 1st of January. There's a gift from mom in the basement, all that sort of thing. But now you take the keys little icon and the yesterday icon. So those are also relations. Out of all dates, some of those dates are yesterday. And of all things, some of those things are keys. So it's a subtype. These are both relations also. So we take keys, and we put it onto thing. We take yesterday, put it onto date, and we find all the places where our keys were yesterday. Or you might have a shell for your calendar, your address book, all that sort of stuff. If there's some public information repos, those would be available, hopefully. So maybe there's a famous, like in Tim Berners-Lee RDF article. He says, I want to find cardiologists who fit my availability and who take my insurance. You want to be able to just say that. And so maybe if you could turn that natural language into a wiring diagram, that might be a kind of middle ground. So suppose there's this internet published doctor cell, and one of its ports is called specialty, and you connect the cardiologist port to the specialty port, and you connect the doctor's availability port to your calendar's availability port. You connect your insurance port to its insurance port, the doctor's insurance port, and then you output, out of all the possible things the doctor cell tells you, you just expose two of them, namely the doctor's name and their phone number. And that would be a wiring diagram where you would just kind of find all cardiologists who fit your availability and take your insurance, and you'd know their name and phone number. So that's the first game. In the second game, I'm imagining like a smarter social network. So it's another simplification of the detective game. And here the cells aren't inhabited by tables. They're inhabited by wirings of other cells. So the idea is that people blog concepts built from simpler pieces. Instead of kind of writing text, they write these little pictures. So they say like, anyone who is named Donald Trump is, this kind of person or whatever. And they form this kind of person by putting together simpler ideas. So others, when I'm reading what they did, when they said something, and I want to know like what they meant, I can disassemble, I can zoom in to their concept and see, oh, they're putting things together like this. And I don't know if it's possible, but it'd be nice if you could like see what was trending in terms of concepts instead of hashtags. So like, I don't know if this is at all possible, but the machine might find concepts that people keep reusing. Like, for example, not in terms of Twitter or whatever, logic gates are particular wirings of transistors, but we don't want to look at the transistors. We want to look at wiring. We want to look at ands and ors or adder circuits. So these are extremely popular wire. Like the adder circuit is a really popular wiring diagram of NAND gates. So out of all the possible configurations of NAND gates, most of them are trash, and as far as we know. But adder circuits are really great. So they're reused over and over and over. And so is it possible that like for human concepts, we might want to find reusable ideas or memes that are just used over and over, somehow put together, and this is just a very powerful concept in human life for some reason. Okay, here's another game. It's pretty different. So it's called the partitions puzzle game. So maybe you could try putting those pieces into that puzzle to get that. So you're allowed to turn the pieces, and you're allowed to put them into the puzzle any way you want. So when you're all done, the bottom thing will just be kind of, you'll try to get this puzzle. I don't know if that's even possibly doable by humans or if you have to really practice or not. But let's see. So let's just take that bottom cell there on the left, bottom left, and put it into 3. You can see it will do something good because it'll connect the bottom thing to that port that's just kind of dead there, and it'll make the thing we wanted here. If we put this guy into 3, we do get this. And then what else is happening is that this port here is being connected to that one. So that looks kind of good because then this thing is connecting up to here, so we just need this one to connect there. And so the solution is this. So I don't know if people would enjoy a game like this, but the point is, they might. They really could, and they really might not. I actually have no idea. But the point is that this is still a case of regular logic, the game. It's exactly, so what is this? It's pretty easy to describe this Ajax functor, whatever. So the type, all the ports are unlabeled, so the type is T is unit. And for each element n in cospan, you make P of n be the set of partitions. What each of these things is a partition on, say this guy's a partition on 6 elements, 5 elements. So these 2 things are connected, those 2 things are connected, and that thing is unconnected. So that's a functor. The set of partitions is ordered in terms of some things are more connected than others. And this is just what's called the poset reflection of cospan co 0, comma, blank. So it's actually very easy to specify. Once you have this language, it'll be really easy to make this game. Boolean circuits are special cases of Boolean relations. So Boolean relations are just subsets of Booleans to the n. So and, or, implies, not, true, false, those are all Boolean circuits. But there are also relations like less than. So true is less than true, false is less than true, and false is less than false. And you can form these guys. You could have puzzles that build up complex relations using simple parts. For example, the less than can be composed as implies true. You stick those 2 things together, implies true, and you get that something that if A implies B is true, then A is less than B. So for example, every Boolean circuit can be made out of NAND gates. So you could, I imagine that there are kids who could have, I think I was a kid who would have fun playing with something like this. So I think there are kids who would still, even in this modern world, who would have fun playing with this. Another game, so you could solve arbitrary systems of equations. So let's say you have F1 of TUV, F2 of VWX, F3 of UWXY, and F4 of XZ. they're all equal 0. So maybe the cosine of t plus the sine of u times v equals 0 and stuff. And we want to find all solutions to this simultaneous equation, all simultaneous system of equations. So I want to know all t, v, z triples, the exposed things, such that there exist values of u, v, w, and x, making all 4 equations 0. What a kind of weird thing, as an aside, is that you can use matrix multiplication to do this no matter how complicated your equations were. So if you plot the equations, say you plot f and g, and you plot them in some range, and you think of that plot as a matrix of on-off pixels. So a plot is like a black and white picture. Think of all the black parts as 1, and all the white parts as 0, and that's a matrix. It's just a big matrix. It's a pixel matrix, but that's, I think, how your screen is probably getting the information. I don't know. So now I just want you to plot f of x w equals 0 and plot g of wy equals 0 as matrices. Plot them. Think of the black as 1 and the 0 as on, as off, white. And if you multiply those two matrices, what's surprising is that you get the simultaneous solution. So here's the matrix for x squared equals w. Here's a square matrix for w equals 1 minus y squared. And if you multiply them using usual matrix multiplication, then the one where one thing is true, that one that's black there, multiplied by where that other thing is true, gives you the row and column of a point on the circle. So you get the simultaneous solution of x squared equals 1 minus y squared, which is a circle. So you can take equations and plot them and multiply those plots as though they were matrices. So it works even if you have non-differentiable matrices, or they're actually called tensors, but they're just arrays of 1s and 0s. And so you could plot all 3 of these things and just multiply the result, and you get some weird picture. Instead of using Newton's method, which is what people usually do, this gives you all of the solutions in your bounding box, rather than just one solution. So again, I think there could be kids who would have fun playing with this. I don't know. I would have just like adjusted things and seen what weird pictures I would get, and maybe I get tired of it after like a week or something. But I think it's just a game that you could play. Monoids, groups, rings, modules, each of these has an associated algebraic theory. So for any algebraic theory, or more generally regular theory, you can work with it. So you have, let's say, the theory of commutative monoids. What does that mean? You have this unit cell called E, and you have this multiplication cell called times, and you can connect them together, and you have equations like this first one represents commutativity, the second one represents unitality, that E times anything is itself. The third one represents associativity. And these look like just kind of mere pictures, but this actually has direct semantics inside of something that actually gives you regular theories and algebraic theories and stuff. So maybe the machines could learn common moves. That's probably hard. Like it's hard to teach a machine how to prove things in Coq or something. But in regular logic, you have so many fewer moves that maybe it's possible to have it find common proof strategies, or encode simple things like x times e is x, just automatically doing that. So within the cells, you could create new cells, and within the game, you could create these new cells like orthogonal and transpose and axiomatize them. So you could define orthogonal, like if you know what an orthogonal matrix is. It's one whose transpose, when multiplied by it, gives the identity matrix. Orthogonal matrix, these are the things that kind of rotate the plane, are those whose transpose multiplied by themselves is the identity. And you can write those things out, and now you can kind of prove things about orthogonal matrices by sticking them into wiring diagrams and manipulating them. So maybe like foldit for protein folding, maybe, and I have no idea how successful that's been. Maybe players could help prove things mechanical Turk style without understanding what's actually what the logic is supposed to be encoding. They're just kind of popping things together and using axioms. Another game, Simulink. So the makers of MATLAB made something called Simulink, and they modeled dynamical systems. And basically, you wire together dynamical systems. So in terms of what this means, like there's something called temporal type theory, which is a topos, and any topos is a regular category. So this actually lives somewhere. But the point is not so much to actually encode that into this game. The point would be just to use reglog as a shell for Simulink, where it would just, Simulink would be the back end for the same sort of pictures. And the final one I'll talk about is neural networks. So neural networks are formed out of addition, scalar multiplication, ReLU, and 1. And they satisfy lots of relations, like if I add two numbers and I scalar multiply, that's the same thing as scalar multiplying and adding. But those aren't relations about neural networks. Those are just relations about the things that neural networks are made out of. So scalar multiplying by s and then by t is the same thing as scalar multiplying by st. If I take something and multiply it by 0, I basically throw away the input. I don't care what it is. It could be anything. But the output is 1 times 0. And if I take anything and I ReLU it, so ReLU means you take an input, a real number. If it's less than 0, give back 0. If it's greater than or equal to 0, give back the number. So if I ReLU twice, I get the same thing as ReLUing once. It's idempotent. So that's what's drawn there. ReLU and then multiply by s is the same thing as multiply by s and ReLU. ReLU 1 is 1. And then these weird relations that I'm not, well, one on the right says, if I'm the ReLU of something, so this ReLU is going backwards. If I'm the ReLU of something, then I'm the ReLU of myself. That's what the one on the right says. But you can presumably work out a sound and complete set of axioms for these 4 things. That'd be kind of interesting to me. But anyway, you can build and play with neural networks. So users could just be building things in the same world they're doing, where are my keys? They're also doing Simulink. They're also doing this. They're also playing with equations. So they're just drawing pictures, but this is a picture of a neural network that takes 3 inputs and kind of multiplies them by weights and biases and ReLUs and stuff and gives you some output. So this is one layer neural network, I guess. But then you could invent other relations if you feel like it. These would all be left adjoints or whatever. These are all directed, whereas you can make things that are undirected, where some of the things go forwards and some of the things go backwards. So for example, A is less than B, you could form out of these units. You can form it as if B plus something equals A, and that something ReLU'd is 0, then B plus, it's got to be a negative number, so B plus a negative number is A, and I guess that means that B is less than A. Or A is less than B. B plus a negative number is A. Great. Okay, so this thing is defining less than out of the pieces that neural networks are formed out of. I'm not saying that you could train less than in this way, or that you can use the same sorts of things you use in neural networks. Maybe, maybe not, I don't know. But I'm just saying that the same sorts of pieces can form lots of different relations, and you could play with it in different ways. And maybe it would be useful in neural networks, but I don't know. So to conclude, I'd love to see this get implemented. So if someone wants to get involved, like, let me know, and I'm happy to help support it. And again, Opali could serve as like a first approach, because what Opali is instead of, well, I don't actually know. All I know is that on his webpage, on Hackage or whatever, it says this was inspired by work of mine, and I know which work he's referring to. So that's all I know. I don't know whether inspired, how much that means is actually mathematized or what, but. So in that work, cospan co sub t, the 2 category, was a 1 category called cospan. I didn't have the 2 morphisms, and I didn't have the co. Sorry, I didn't have the 2 morphisms, and I didn't have the co. And the poset was just set. It wasn't a 2 category posets, it was a category of sets. But cospan fits inside of this bigger cospan-y thing. And poset, the 1 category, fits inside this bigger poset-y thing. So the Opali thing fits inside of this to the extent that the code actually follows the math. So again, every TP pair constitutes a different game in this reglog game. It's not just database querying like Opali, but playing the game would involve wiring up cells and seeing how they relate. This is just a kind of summary slide here. And again, there are as many games as there are regular categories. And I didn't say it yet, but there are also morphisms of games. So if you have T and I have T prime, and your P maps to my P prime somehow in this way, then you can take all of your cells and turn them into my cells, and all of your wiring diagrams will become my wiring diagrams, and all of your entailments will become my entailments. But I'll have more of everything, or some things will be collapsed. I think it would benefit a lot from dependent types, but again, I'm not a programmer, so it just seems like there's dependent types everywhere. You pick your T first, and then you get your P. But inside of the co-span thing, there's like, you pick the type surrounding a little shell, and then you pick a subset of it. So it's lots of like these layered things. So yeah, if in the future you have questions or ideas about this or anything category theoretic, feel free to email me. And that's it, so thanks.